So we've been talking about continuous growth and continuous decay, but if you recall, the name of this section was about logarithms, so it's probably time that we actually talk about logarithms. So a logarithm is it's a function. It can be used as a function at least. And for x greater than 0, we have the base 10 log of x, and that's called the common log. One of the weird things about logarithms is that there are special logs that have special names, and this is one of them, the common log. And it's defined to be the following thing. Y equals log of x is equivalent to x equals 10 to the y. So that's key for understanding what a logarithm is that anytime that you have a logarithm, you can convert it to its exponential form. And in theory, anyway, the exponential form is sort of easier to understand. So the conversion is always that we take the argument of the log, and then that becomes the output over here. And then there's actually one thing that's maybe a little bit confusing about this is that the way it's written here is that the actual way to write this is like this. Y equals log sub 10, that sub is a base, log base 10 of x, and that's equivalent to x equals 10 to the y. But this logarithm is used so much that people just kind of got lazy and stopped writing the 10, and it's just oftentimes just written exactly like this without even expressing the base. But if you see a log and there's no base written there, then you can assume that the base is 10. So what I was saying was I was going to talk about the converting from the log form to the exponential form. Let me go to the whiteboard and we can do some more of that. So if I have y equals log base 10 of x, this is equivalent to x equals 10 to the y. So the base here is the base of this exponential over here. So that hopefully that makes sense. And then this y is actually the exponent. Okay. So this is actually usually written, so log base 10 is written just plain old log. I guess I put a variable in there. Log base 10 of x is written just log of x. Okay. And that's called the common log. So this conversion is a good way to understand a logarithm. So for example, because sometimes it's kind of hard to understand like what this is saying. So if I have, say, log base 10 of 3, that equals y. Well, the exponential form of this is 10 to the y equals 3. So in other words, we're looking for the y value that when we raise 10 to that y value would give me 3. And that's what this output would be. Now, I don't know what that is because it's going to be some decimal value that that's not an easy value to compute. So I would have to go to the calculator to do that. But in any case, that's what it's asking. I can write down one that's actually easier to compute, like this. Say, what if we had log base 10 of 100? Well, the exponential form for that is 10 to the y equals 100. And I actually know the answer to this one just from first principles. I know that y has got to be 2 there. So the takeaway from all of that is that log base 10 of 100 is equal to 2. So some logarithms you can just compute by hand if you happen to know this solution. Okay. All right, so back to this slide. We define this log base 10. Right underneath here we have another very important log, arguably more important log, especially for us, and that's the base e log. Okay. So we know we've got this e value that we've been using for continuous growth and continuous decay, and that's what we're talking about when I have base E. I'm talking about 2.71828, and so on and so on. Okay, so the base E log is actually called the natural log, and the definition of the base E log, and again, it's written in a weird way, so the actual sort of function way to write this would be log base E of x, right? Log base E of x. But this is used so much that over the years it's been simplified, and instead it's just written y equals ln of x. So ln of x means log base E of x. And these are equivalent forms. This is not the exponential form. This is just another way to write the log base E. The exponential form of this, and that's what you see right here, is, and you can see it better if you write this version, because the base E raised to the y equals x, or other way around, x equals E raised to the y. So that's the exponential form. And this is both of these are the log form. Okay. Now, as I was doing with the other one, I could put down some values here, although E is a little bit harder to work with. So like, before I had y equals log base 10 of 100. If I do log base E of 100, but we should get used to writing this in the proper way. So if I write y equals ln of 100, the exponential form of that is e to the y equals 100, and I have no idea what the answer to that is. I mean, I could roughly guess it, like what power of e would give me 100, but I don't know it off of the top of my head. I'd have to calculate that. So there's just not as many easily computable values with e as there are with 10. However, we are going to use the base e version a lot more, because that's the one that's typically used in terms of continuous growth and decay, which, as you know, we have been studying. So ln of x is going to be the one we use all the time. And you may remember that I've talked about this in regards to the calculator a little bit. You have two buttons in the calculator that are important in regards to logarithms. This is one of them, and this is the other one. So this one is log base 10. And let me stress that again. This is not just log of whatever. This is log base 10, and only log base 10. And this ln is log base e. So that's the natural log here, and this is the common log. So we have dedicated buttons for log 10 and log e. Any other log, you don't have a button for that. And frankly, we're not going to be dealing with those other log bases, so I'm not going to worry about it. That's more of an issue you would handle in pre-calculus. Okay. So we've got log base 10, log base e, and we're pretty much just going to be working, honestly, with just log base e. You can't really study logarithms without talking about inverse functions. And the reason for that is because logs are inverse functions, in fact. They are the inverse function of the common log is the inverse function of the base 10 exponential function, and the natural log is the inverse of the base e exponential function. And now that shouldn't be that surprising, considering that when I define these two, I immediately converted it to an exponential form for each of them. So there's certainly a connection there. Now, as this slide is saying, notice how, like, for the log button and the ln button, the second log gets me the inverse, and the second natural log gets me this inverse e to the x, or 10 to the x. So you've got your inverse functions right there with the original functions. And remember that an inverse function undoes what the original function did. Okay. So in a full pre-calculus class, you study logs and logarithms for a long time, and you learn a lot of properties, and do all sorts of problems with them. However, we're only interested in a few properties of logarithms. I'm going to specifically be talking about base e log properties. although all of these log properties are actually true for other bases. It's just that base E is the one that we're going to be using the most. So here's the first three. Number one, ln of e to the x is equal to x. Okay, so this is actually, in truth, what this is it's an inverse property. And the reason this is an inverse property, and this may be going a bit deep mathematically, but I'm sure some people are gonna follow this, so I'll go ahead with it. So if I write the full version of this, this is log base e of e to the x. And so if you remember what an inverse function does, it's you compose the function with its inverse and you just get the variable. So what we've actually done here is we've composed the log function with the exponential function, and it just spits out the exponent, which was the original variable. Now, number two is also an inverse property, but it's just the other order, or in the other direction. So if this is like f composed with g, then this is like g composed with f. And it's e raised to the ln of x equals x. Okay? So those are both inverse properties. This last one, it doesn't have a specific name, but I'm going to call this the power to product. Because if you notice what happens when you take the natural log of a value raised to the x power where the base is larger than 0. If you take the natural log of this, it kind of pulls down the exponent and converts that power to a product, so a multiplication. And then you still have ln of b, so you still have ln of the base. Okay, so those are my three properties that I'm going to be using. I'll give you an example right here of how we could use these properties. So here's an equation, and I'm going to solve this algebraically, okay, at least as much as I can. So I've got 378 equals 1.0317 to the x equals 900. Now this is a exponential model, an exponential equation. And there's an interpretation down here in terms of sort of math modeling. But if I just approach this as a equation to solve, my first step is I'm going to divide both sides by 378. Okay. And then I have this fraction. And now I am going to take the log. I'm going to take the natural log of both sides. And what I mean by that is we're going to take this left-hand side and put it into the natural log, and we're going to take the right-hand side and put it into the natural log. And when you do that, you don't change. I mean, that's a legal move, mathematical move to make. So in other words, I'm going to do this. ln of 1.0317 to the x equals ln of this fraction 900 over 378. And you may say, well, what does that do? Well, if you remember the third property, I know we just learned it, but that third property, power to product, means that I can bring the power down, which is the variable. Of course, I'm running out of space, but I'll bring my variable down. And I've still got this ln of this fraction here. And now I can actually solve my equation. So I'll solve it on the whiteboard. I might run out of time here on my video. Let me kind of quickly try to knock this out. So x equals ln of 900 over 378 divided by ln of 1.0317. Now, yeah, that is kind of a mouthful, and I've got to put all that in the calculator. And you've got two natural logs in the numerator and the denominator, but that's it. So I'll actually calculate this. I'll put this in the calculator in the next video. So I'll pause the video here.